We're now moving forward from the previous video and to discuss events that are defined in a limit. We have been discussing the existence of a probability space where a coin can be tossed infinitely many times. We discussed a serious issue about defining the expectation by two separate sentences as if random variables belonged to two different worlds. And we have discussed how nice it would be if you could just differentiate inside expectation. Now let's define a few relevant events that are defined in a limit. First one, the ruin probability. Suppose we go to a casino with initial cash x naught belonging to the set of natural numbers including 0. Of course, casino here is just a silly representation. We can be an insurance company paying claims to our customers. So let's denote by xn the balance that we have after we've been betting for n rounds in this casino according to some given fixed strategy. If at any point our balance is 0, then our balance remains 0 forever after, because the casino does not take bets from customers that are bankrupt. And suppose we wonder what's the probability that this event occur. What's this event? Well, that eventually we get 0 balance. And well, the first consideration we make here is that in order to stay in this state 0 eventually, which means we achieve this, it means for some n we get capital equal to 0, and here's the union that represents the concept of for some n, and then here for every m larger than n our capital is 0. So we're talking about this union of intersections indexed by the variable in the first union of events. So this is also an event that follows from the property of events, and this is the event we're interested in represented in a more tangible way. Then, using properties of probability measures, such as the fact that this event inside here, indexed by n, is increasing in n, then what we really have is an increasing family of events, and we're taking the union over an increasing family of events. Then we can compute the probability of this event simply by taking the limit of the probability of these events here indexed by n. And well, it turns out that because of this property here, we can remove the intersection and just put n here. So this is how we got this event here, and we got rid of the intersection. Now here's another question. The strong law of large numbers. We have a sequence of independent random variables. Let's say they take values plus or minus 1 with probability 1/2. And we count how many of those took value plus 1. We count how many took value minus 1 and subtract. Well, the law of large numbers, it says that this sum here, it will tend to 0 as n tend to infinity, and that this event has probability 1. How could we possibly approach this event in a way that we would be able to compute its probability? Well, we start by expressing this event as a limit of other events that are more tangible, and then we compute its probability that way. Let's do only the first part here, which is expressing this event as a limit of other events. So what does it mean for a sequence to converge? Well, let's refresh our knowledge from calculus or analysis. For a sequence to converge, we have for every epsilon, there exists some n naught, such that for all n larger than n naught, such and such and such. Well, first we can replace epsilon here by k, and then instead of epsilon here we can have 1 over k. That's convenient because we want to deal with countable sets. And then that means for every k, there exists n0 such that for all n larger than n0. So we see this is for all, there exists for all. And we have this event here. And this is a very concrete, tangible event. The average of these random variables, the absolute value was less than k. So we see here all these unions and intersections of events that are more tangible, that allow us to express an event of interest. And we can compute that because these sequences, they are either increasing or decreasing, and then we are taking either the union or the intersection respectively. So we can, in fact, compute this probability as a limit. More about this relationship between convergence of random variables and condition on one of them being less than a certain number will come in week 8. For more examples of events that are of interest and that require some type of limit to be approached, you can see in the lecture notes.